In this lesson, we're going to look at the all-important distinction between a process and a thread. The working file you're looking at is called processthread.txt. So to begin, the traditional and still very good definition of a process is a program in execution, but the point should be made that a process is really an abstraction. It's meant to cover all of the things that go on in a computer system when a program executes. In particular, a process as an executing program requires lots of resources. In particular, it requires, of course, at least one processor to execute the code. It requires memory to hold the instructions and the data that make up the program. And typically, but not always, it requires I/O devices. So some special purpose utility processes require, of course, a processor and memory, but they may not need any I/O devices. Now, when you execute a program from the command line, so I'm showing a Windows type example down here, hello world. When you execute that program at the command line, basically what you're doing is starting a process which then executes, in this case, to completion. The most important feature of a process from our point of view is that every process has its own address space, and that address space is made up of all of the memory locations that the process can legitimately touch. If a process goes out of bounds, on different systems you'll get different error messages, but segmentation fault is a common one. But if a process goes out of bounds, it tries to hit a memory location not within its address space. The typical result is that the operating system puts the kibosh on the process. It aborts the process immediately. The important thing about separate address spaces is that these partition processes, in their natural state, you might say, one process cannot step on the memory of another process. So there's safeguarding of memory automatically with processes. Now, the notion of a thread is more recent than that of a process, and it's a little bit trickier, and I'm going to introduce it with an example. Suppose you have a program that has 50 instructions. You could treat that program as one thread of execution consisting of 50 instructions. So a thread is just a sequence of executable instructions. A thread, by the way, is what a modern operating system, whatever the variety, will schedule on a processor. So you could take the same program with the 50 instructions, and you could break it up, for example, into 5 threads of 10 instructions apiece. That seems reasonable. You could go to the extreme and break it up into 50 threads of 1 instruction apiece, which would be quite unusual. So a thread for our purposes is just a sequence of executable instructions that can be scheduled on some processor. Now, in terms of definitions, every process has at least one thread. If a process has only one thread, it's single-threaded. If a process has more than one thread, it's multi-threaded. How exactly we partition the instructions in a process into different threads is something that we'll push back until later. We'll see lots of code examples that do this, but for now, it's the concept that's really, really important. Now, the tricky part about threads, and we'll go over this many, many times, we'll have various code examples. The tricky part about threads is that threads in the same process share the same address space. And this means that threads can touch one another or touch the memory locations accessible to one another in bad ways. When that happens, there's a nice phrase to describe it. It's called a race condition, although, as we'll see, the race is a little bit unusual. So suppose you have, in a single process, 5 threads, and each thread is executing this instruction, n equals random underscore num. That's a function that generates some random value. N is a shared memory location. Now, if all of the threads can hit this, and if all of the threads are executing at the same time, that's the visual you want to have. So we have a multiprocessor machine. The results are going to be unpredictable. Indeterminate is the term sometimes used. So a race condition is going to result. What's unusual about this race condition is that the last thread to update n is, in effect, the winner, because it's that value that's going to be the value of n. For now, the general idea of a race condition is good enough, but we'll illustrate this any number of times with code examples. So let me wrap up this introduction to threads and processes with a very simple depiction. So what I've shown at the bottom of this text file are two processes. I'm just calling them Process 1 and Process 2. Process 1 consists of 2 threads, Process 2 of 3 threads, so each process is multi-threaded. I'm assuming a multiprocessor machine, so Process 1 is scheduled on Processor 3 in the following sense. One of its threads is scheduled on that processor. In this simple depiction, Process 2 has one of its threads scheduled on Processor 7. Now, if we have sufficient processors, suppose, for example, we have 8, then it's possible, of course, that all 5 threads are executing simultaneously. And this is the sort of challenge that we're going to be looking at pretty carefully. So, in summary, a modern operating system schedules a process on a processor in the sense that it schedules one of the threads in that process on a processor. Every process has its own address space. They're effectively partitioned from one another with respect to memory, but threads within a process share an address space, and a challenge for a programmer in a multi-threaded process is to coordinate the threads so that bad things don't happen. The bad things come generally in 2 flavors: race conditions, which we've seen already, and deadlock, which we'll see later. So, that wraps up the first technical look at processes and threads. This is a topic to which we'll return many times, but in the future in the context mostly of examples.